Welcome to qnawire.
Hi, so in this case, what we're going to do is add HCl to a solution of NH3. So the reaction that we're going to have is NH3 in aqueous solution plus HCl. It is going to produce NH4 plus Cl minus. So in this case, after the reaction happens, we're going to have a buffer. And since we are going to have a buffer, we're going to find the pH with the Henderson-Hasselbalch equation. So first thing that we need to do is from the Kb, that is equal to 1.8 times 10 to the minus 5, we can find the pKb, which turns out to be 4.744. Well, 745, let's round it up. And knowing that pKa plus pKb needs to be equal to 14, we know that the pKa will be equal to 9.255. With this out of the way, we can proceed with our ice table. I'm going to do the ice table in terms of amount of mole that I need to add, because we don't know how much of HCl we need to add to the solution. In this case, initially of NH3, I'm going to have 0.1 mole per liter of solution. Of HCl, I'm going to call this quantity X because I don't know how much that is going to be. And I'm going to start with 0 and 0 of each of them. The limiting reagent, of course, is going to be the HCl. So the amount of change is going to be minus X on both sides and plus X over here. Thus, at equilibrium, I'm going to get 0.1 minus X, 0, and X. All of this in terms of moles. Now, in the Henderson-Hasselbalch equation, we know that the pH needs to be equal to pKa plus the logarithm of the concentration of the conjugate base. In this case, the base is NH3 divided by the weak acid, which is NH4 plus. We can directly employ the amount of mole in the Henderson-Hasselbalch equation because we know that NH3 divided by NH4 plus, this is going to be equal to amount of mole that I have of NH3 divided by the total volume divided by amount of mole of NH4 divided by the total volume. So at the end of the day, it is not going to matter the total volume of the solution because they are going to cancel out when we have the coefficient of the concentrations. So now what we are going to do here is replace the values from the equilibrium concentrations that we found. In the case of NH3, this is 0.1 minus X. And in the case of NH4 plus, this is equal to X. So with this, our equation becomes pH needs to be equal to 9.255 plus logarithm of 0.1 minus X divided by X. And the pH desired for our solution is 9.53. We can rearrange this equation, take the numbers on one side and leave the logarithm of the other. We are going to get 9.53 minus 9.255 on the left hand side. So 9.53 minus 9.255. This is equal to 0.275. And this is going to be equal to logarithm of 0.1 minus X divided by X. Rearranging this equation and getting rid of the logarithm, 10 to the 0.275 will be equal to 0.1 minus X divided by X. From here, X times 10 to the 0.275 is equal 0.1 minus X. Let's put all of the X's together on one side. X times 1 plus 10 to the 0.275 needs to be equal to 0.1. Thus, the value for x will be 0.1 divided by 1 plus 10 to the 0.275. After doing this operation, the result is an amount of mole of 0.034678. And what is this x? That x corresponds to the amount of mole of HCl that I need to add. This is mole of HCl added. But we wanted to know the volume, and we know the concentration, right? So, from the molarity equation, molarity is equal amount of mole divided by volume, we know that the volume is going to be equal to the amount of mole divided by molarity. So we're going to put this number, 3.46783 times 10 to the minus 2 mole, divided by the molarity of my solution, which is 0.1. This is the same thing as multiplying by 10. And the result, it is going to be given in liters. The volume then, in order to get that solution, is 346,783. So 0 point liters, corresponding to 346.78 milliliters. So that should be the final volume that I need to add of HCl with a 0.1 molar concentration.